All right. So the next chapter in the Klein textbook is all about addition reactions, or essentially like elimination reactions in reverse. So we'll go through this, and a lot of these are actually very, very intuitive. So let's go and review elimination reactions. And we'll try to review a little bit as the term goes on. But in an elimination reaction, you have typically some sort of alkane with a leaving group coming off of it. So you could label this as an alkane or a functionalized alkane. And what else do we need to have if we're going to do an elimination reaction? A base, right? So typically in an elimination reaction, you want a strong base. Usually it's something with a negative charge. And you would have one of these beta protons hanging off. This base can grab this beta proton, clamp down, and eject off your leaving group. So if this happens all in one step, would this be an E1 reaction or an E2 reaction? E2, exactly. So in these reactions, oh my goodness, I'm going to close this and restart it. This keyboard keeps on popping up. All right, so in this reaction, you're going from an alkane to an alkene. We're not going to review too much about this, but make sure you do remember whether or not you'll get your Hoffman product, your Zaitsev product, what your regiochemistry and stereochemistry would be for these types of reactions. All right, let's compare this to an addition reaction. All right, in an addition reaction, you're going to start with an alkene, and you're going to react it with some sort of nucleophile. I'll just call this X and Y. And you'll be able to add both X and Y across that double bond. So instead of going from an alkane to an alkene, you'll go from an alkene all the way to a functionalized alkane. All right, entropically, which reaction do you think is more favorable? The top one or the bottom one? The top one, right. Why do you think the top one is entropically more favorable? Does anybody want to share? The moles, right? So if we look at elimination, we're starting out with 2 moles of our reagent, and we're spitting out 3 moles of our products, right? On the bottom one, we're starting out with 2 moles, and we're going to 1 mole. So the top one, meaning elimination, is entropically a lot more favorable than an addition reaction. So like we said with elimination chemistry, we normally do that under high temperatures. With addition reaction, do you think high temperature is very favorable? No, exactly. So let's make a note of that, that this is typically run under high temp in order to take advantage of entropy. Or the bottom one, because we're actually getting more ordered, we don't want high temp, we want low temp. So a lot of these reactions that we'll see this term, if you were to perform them in a chemistry lab, you would run these under ice bath conditions or even below ice bath conditions, so below 0 degrees Celsius. All right, the weird thing with addition reactions is that your pi bond acts as your nucleophile. Oh, come on. So in addition reactions, the pi bond of your alkene acts as a nucleophile. This is a bit different than what we saw last term. Last term, we normally saw lone pairs acting as a nucleophile, but in this case, we're going to be using the pi bond. So for example, the first step for a lot of these reactions will involve that pi bond reaching out and attacking some sort of electrophile. There's a whole bunch of variations of this, so I'm going to leave this arrow out for now, but that's the key takeaway for an addition reaction. Any questions so far? All right, so we'll start with the easy one. First one we're going to look at is called hydrohalogenation. And just like before, we're going to have some sort of alkene, which I stated was our nucleophile. That means it has high electron density. And in this reaction, we're going to treat this with hydrobromic acid, or HBr. However, I did want to make a note of this, that this also works with HCl or HI. However, most of what we'll see is with hydrobromic acid, it's the most common one. And in this reaction, hydrobromic acid is going to act as our electrophile. And what's the fastest reaction that occurs in chemistry? Acid-base chemistry, right? All right, so now we've got our nucleophile that can reach out, grab the proton. We know acid-base chemistry is going to be the driving force of this reaction. And we're going to kick off bromide as our conjugate base. All right, so now we've got a few things to consider. First one is we could have the proton come off that center carbon, or we could have it come off that right-hand carbon. Which intermediate do you think is more likely? Which one? The right one? Why is that? It's a secondary carbon, right? This one is a primary carbocation. This one is secondary. We always prefer to go through the more stable intermediate because it has the lower activation energy. So this one's very unlikely to occur. So the secondary carbocation's a lot more likely. All right, like we said, bromide is our conjugate base. So that's also floating around. It's kind of the leaving group. And this bromide can act as a nucleophile and attack that carbocation, and it could attack from the top lobe or bottom lobe of that p orbital, right? So there we go. We've got a functionalized alkane. This time it's a bromine. However, if we used HCl, we'd have a chlorine there, and if we used HI, we'd have an iodine there. So like I said, conceptually, a lot of these reactions we're learning this term aren't super over-the-top challenging. It's just more remembering all of the different variations of them. All right, so the main takeaway for this reaction is you always want to form this more stable carbocation. All right. We also have some new terminology that we're going to throw around. This is referred to as Markovnikov addition. And Markovnikov addition is just named after the scientist that was studying these addition reactions. It's pretty easy to remember. Yeah, it's easy to remember because basically it's just saying you're going through the more stable carbocation intermediate, and conversely, your nucleophile, meaning the bromine, is going to be attached onto the more substituted carbon. This reaction does get fairly tricky though, especially when you're starting with, when you're starting with pretty unique alkenes. And what I mean by that is you have to watch out for stereoisomers. So what are the two different types of stereoisomers? Who remembers? Enantiomers and what was the second one? Diastereomers. So with this reaction, you might run into getting mixtures of enantiomers or diastereomers. All right, so let's do a more challenging example. Sorry, my screen's kind of glitching here. I'm not sure why it's doing that. And in this harder example, we'll use a more substituted alkene. And hydrobromic acid. And just like we saw before, we're going to use the alkene as our nucleophile. So the arrow always starts from the alkene, and we'll grab a proton off of hydrobromic acid, and we'll kick off bromide as a leaving group. All right, just like before, we'll compare our two different potential carbocations that we could get. We could get one where the hydrogen adds to the right side of the alkene, and you get a carbocation right there. Or, let's compare the alternative. You could get one where the hydrogen adds to the left side of the alkene, and your carbocation's right there. Which one's more likely, the left or the right? The right. Why is that? It's more substituted, right? So just like we saw before, secondary compared to tertiary, tertiary is going to be more stable and it's most likely going to occur. So we can cross this one out as being the unlikely intermediate. And just like before, we're going to have bromide floating around. All right? So bromide has a few options here. One could be that it attacks from the top. So I'll just write this as top face attack. And we can show this product down here. If it attacks from the top, that means it's going to be coming off as a wedge, right? And the methyl group is going to be pushed into a dash conformation. Conversely, this bromide could attack from the bottom. And if it attacks from the bottom, we're going to get something that looks very similar. But this time bromine will be coming off of the dash and the methyl group will be a wedge. All right? Which one do you think is more likely, or do you think they're equally likely? Yeah, I'd say equal, right? Let's think about the geometry of this carbon right there. What's the geometry? Trigonal planar, right? So it's going to be flat like a pancake. The bromide can attack either the top side of that pancake or the bottom side. Doesn't really have a strong preference either way. So if we think about this, we're going to get both of these in about a 50-50 mixture. What's the relationship between these two products? They're enantiomers, right? So we could say that this is a equal mixture of enantiomers. And what do we call that when it's an equal mix? It's a racemic mixture. Is this mixture of products going to be optically active? No. Just like we saw first term, if you have a racemic mixture, yes, you do have two chiral products, but they cancel out plane polarized light, and therefore you have no net optical rotation, and they're not optically active. So we do have to watch out for enantiomers and diastereomers. In this case, we're getting a mixture of enantiomers, not diastereomers. Does that make sense? All right, let's try another one. All right, so this one we've got an alkene, we've got hydrobromic acid. Just like we saw before, this alkene can grab this proton, clamp down over here. And we've got a few options. We could show this one right here where we get a proton coming off that lower carbon plus a proton coming off this upper carbon. All right, which of these do you think is more likely to occur? They're both secondary, right? So they both could occur. They're both secondary carbons. So we could run into a situation where, hey, maybe bromide attacks into this one. It could attack from the top face or the bottom face. I'm not going to worry about stereochemistry here. So that could be one potential product. What do you notice about the top, or sorry, this product on the left? Can it do anything to stabilize itself? It could rearrange, right? So if we think about the top one, we do have an option where before rearrangement, this bromide attacks in. And I'm just going to label this as the no rearrangement product for both of these. However, we could have an alternate pathway where maybe this green hydrogen over here hops over. In fact, I'll use a different arrow to indicate that, to that spot. And we'll just label this as rearrangement. And in this rearrangement, we now have a different position for that bromide to attack onto. It could attack into that top tertiary carbon. So I will say this is one pitfall of these reactions, is sometimes they give you this horrendous mixture of product because you have these different potential intermediates that can occur and intermediates that can rearrange. So sometimes chemists have to be very careful with how they run these reactions. You can control it to a certain extent by changing the dilution of your HBr, but to a very real degree with this reaction, you would get 1, 2, 3 different products out of this one relatively simple reaction. So they aren't always super clean reactions that give you only one unique product. Yep.
For the middle one, wouldn't that one be not very likely though, because it's rearrange take priority or it's more stable?
Yeah, that is a good question. So the question is, wouldn't rearrangement take priority? I told you guys last term that yes, it almost always takes priority. However, if you were to check this mixture, chances are you'd see a little bit of the unrearranged product. It's unfortunate. It does mean that these reactions are messy, like I was saying. What's the relationship between all 3 of these products? They're constitutional isomers. So these would be a lot easier to separate and purify, which is the one saving grace of these reactions, is you can clean up constitutional isomers a lot easier. All right, so that's the main takeaway for this one, is watch out for rearrangements. Oh my goodness. Sorry. I don't know if it's this new projector or my laptop. Come on. Why won't it let me go? All right. Sorry. All right. So watch out for carbocation rearrangements. These reactions can be messy. All right. There is one interesting historical tidbit about these reactions. So the name Markovnikov reactions were in reference to the chemist that was investigating these. A lot of people for a long time didn't really believe him because they couldn't reproduce his results. It was pretty interesting. So I'll show you what was happening. So it's pretty easy to remember the opposite one. They just call it anti-Markovnikov, meaning they didn't get the results that he observed. So he was pretty confident that if you combine this alkene with something like hydrobromic acid, that halogen, like I said, will always come off of your more substituted carbon, right? So this was named after his studies. So this is referred to as Markovnikov addition. However, a lot of other people did these same reactions with HBr and observed something different. They observed the bromine coming off the less substituted carbon. This is called anti-Markovnikov. And so there was this big debate about, well, why are some people observing the bromine coming off of the more substituted carbon while others are observing it coming off the less substituted carbon? And in fact, Markovnikov went back, checked his results, and confirmed that the bromine for him always came off the more substituted carbon. Does anybody have an idea of why there might have been a discrepancy? Yeah, it was the purity of the reagents. What they found was that Markovnikov was using really pure HBr. Other people across the globe trying to replicate his work were getting sources of HBr that were cheaper and less pure, and that they were getting this anti-Markovnikov product. So then people were curious, well, why is this happening? And is there any way to control this? And what they found was that it was one specific impurity causing all of the problem. And that impurity is called an alkyl peroxide. And people like to write it out as ROOR. And R is going to be some sort of alkyl group. It doesn't really matter which alkyl group, but that oxygen-oxygen bond is the key feature there. Peroxides are really unstable. They tend to fall apart and form radicals. So if you take biochemistry, you'll talk about that in a lot more detail. But this actually initiates a completely different reaction mechanism where you get an anti-Markovnikov addition product. The good thing with this one is you don't need to know this mechanism. Right now. Yet. There we go. So because it involves radical chemistry, we're going to kind of lay off on that until we get to that chapter where we talk about radical chemistry in a lot more detail. But the key thing is radical chemistry changes everything about this reaction. Does that make sense? All right, there's also one other note. Previously, up here, I said that HCl and HI work really well for these reactions in addition to HBr. The anti-Markovnikov addition reaction only works with HBr. And again, we'll talk about that when we get into radical chemistry. So it only works with HBr. All right. So we have one more type of halogenation reaction I wanted to cover really quick. And this is one we actually saw last term in one of our labs. And this is just called classical halogenation. So let's take a look at what occurs with normal halogenation. Just like we were saying, pi bonds can act as nucleophiles. And in this time, we're going to be using elemental bromine. This will be our electrophile. Let me erase this S. And a lot of times people will ask me, well, why is elemental bromine, in this case, an electrophile? There's not even a net dipole. And it's a really good question. The reality is bromine is a pretty large atom, especially relative to chlorine and fluorine. That means that it's highly polarizable. What does that mean? You can polarize it. Basically means it has this giant electron cloud. Your electrons can't be everywhere at once. So at any point in time, you're going to have some imbalance of electron density, right? So some people refer to it as a squishy electron cloud or a polarizable electron cloud or just simply polarizable. So in this reaction, your nucleophile can reach out, grab your bromine can attack back in, and you can kick off bromide. So it's a three-step process in terms of arrow pushing. Let me clean this up. And you get this triangle-looking thing. And bromine now has a positive charge to it. This is called a bromonium ion. This just looks wrong intuitively. Does anybody know why it looks wrong? Bond angles are way off of your ideal Vesper angles for sp3 hybridized carbons. We'll talk more about why we think this is the mechanism. The reality is when we're showing a lot of these mechanisms, they're the most probable ones. We can disprove mechanisms, but in this case, this is the only one that makes any reasonable sense to us at this point in time. All right, we still have bromide floating around. And bromide at this point really wants to react with the bromonium ion because it's so wickedly unstable. So at this point, you can think about this bond between each of these carbons as having a huge dipole, right? That bromine is not happy with the positive charge, so it's going to yank electron density away from each of those carbons. So this bromide ion can attack underneath one of these carbons and slingshot open this ring. And the cool thing with this reaction is you only get what's referred to as anti-addition, meaning the bromine on one side will be on the opposite face of the other bromine. So let's make a note. All right, so now let's go back to this funky looking intermediate and try to figure out how they came up with this as being a plausible intermediate. What would the other possible intermediate be if it's not this? Well, let's try the other one. So alternate incorrect mechanism. So let's say we have elemental bromine around. We could just say, well, why doesn't it do a similar reaction to what we just saw with hydrohalogenation? So this alternate mechanism goes through a carbocation intermediate. in our original proposed mechanism, we went through the bromonium ion intermediate. So the question is, well, how can you really experimentally tell the difference between these two mechanisms? They gave us the exact same products, right? If we were to name this product on the bottom and this product right here, they would have the exact same name. That's where chemists have to get pretty clever and creative to determine which mechanism is more likely than the other. So I'll show you a classic example of how they would have deduced this mechanism. Okay, so let's try this example. And I'm going to label all of my substituents carefully. I've got a methyl group, I've got a methyl group, I've got an ethyl group. And what I want to do is I want to imagine this laying on its side. So let's say we've got this carbon-carbon bond right here. I've got an ethyl group sticking back. Got a methyl group kind of sticking forward here. On the left carbon, I've got a hydrogen sticking back. Got a methyl group here. And then we've got these p orbitals coming off of these carbons, right? That are pi bonds. All right, so that's my three-dimensional view of my alkene. If we think about that pi bond acting as a nucleophile, we could use the top face or the bottom face, right? Oh my goodness. Ugh. I don't know if this is a sign for the year to come. Sorry, everyone. Okay, so we've got this important note that both sides of the alkene can act as a nucleophile. Now let's see what happens when we react this with elemental bromine. We could have one product where maybe that bromine installs itself on the top face. So we get this triangle with the bromine coming off the top. We would have methyl group here as a wedge, hydrogen there as a dash, methyl group here, ethyl group. Or we could have the bromine coming off the bottom face of that p orbital, right? Oops, this should be a methyl, not a bromine. All right, we've got bromide still floating around. What's the relationship between those two intermediates? What do you think? Are they the same? I wouldn't say they're the same. They're enantiomers of one another. So they're not identical intermediates, so we do need to account for both of them. But let's just show the next step. So this bromide could attack from underneath, slingshot this open. This bromide could attack on top, slingshot this open. This methyl group is still going to be a wedge. This methyl group will still be a wedge. And then down here it would be a little bit different. So what's the relationship between these two products? Are they identical? Let's think about it, right? Who thinks they're diastereomers? Who thinks they're enantiomers? A few people think enantiomers. Yes, they would be enantiomers. They are non-superimposable mirror images of one another. So in this example, you got a mixture of enantiomers. If we hypothetically went through that carbocation mechanism, we would get 4 different theoretical products, but experimentally we know we only get 2. So that supports this bromonium ion intermediate taking place. Let's make a note of that. If the reaction were to go through a carbocation intermediate, we would get 4 different stereoisomers. Hey.